Hi there. In this video, we're going to talk about some terminology that we need to understand when we're considering the Fourier transform. And those are some terms, for example, amplitude, period, and especially frequency and angular velocity. So the terms frequency and angular velocity are used sometimes interchangeably in the study of the Fourier transform, and they play an important role in the analysis of a function when we take its Fourier transform. So in order to understand this further, it's important to be able to articulate and understand what exactly is the difference between the two and why these terms are sometimes used interchangeably. So if we have a function, some kind of signal, and it could be a sine curve, for example, so we know that this is a periodic function, and we in the time domain, or rather the x-axis is time, and we have a function of time as the y-axis. So we know that when the function starts to repeat itself at a certain time later, right? So that is the period. So the period t is the time it takes for the function to start repeating itself. So we designated that by t. So t could be, for example, 2 seconds. And you would say it takes 2 seconds to complete one cycle. Very related to period is frequency. So we speak about frequency as being the inverse of the period. When we say the inverse of the period, we're saying 1 over t. So if we were to invert what we have just written here in terms of the amount of time per cycle, so what we're actually saying when we take the inverse of the period is the number of cycles that it completes in 1 second. In this case here, we've written half. We've inverted this period. So we're saying half, 0.5. It completes 0.5 cycles in 1 second. So this unit cycles per second is given the name hertz. So we would write 0.5 hertz. So where does angular velocity and all of these things come in? Very often when we consider periodic functions, and we have considered the Fourier series, we have defined all of these things to be in terms of a period of 2 pi. So we often have to convert or consider these signals to be in 2 pi. So how do we relate this time domain to this period being 2 pi? Well, what we do is make the analogy of a circle. So in the analogy of a circle, we know that there's an angle associated with each point along the circle. So starting at a certain point on the circle and going round and coming back to where you started is analogous to, starting at a certain point along a curve, going along halfway, and then ending up back where you started. And we know that the circle has the period 2 pi, or rather the length of the circle, or rather the total distance traveled by the angle, if you are a point on the circle, is 2 pi. Because of course the total angle of a circle is 360 degrees or 2 pi radians. So now we're in a position to convert these units to be in terms of radians, because we want to bring in the 2 pi somewhere along the line. So what we would do is that we consider 1 over t. So remember that 1 over t is frequency, right? Frequency is the number of cycles per second. So we have the number of cycles in 1 second. Also the unit hertz. So how would we relate this to be in terms of radians? Well, we just do some dimensional analysis. We have cycles, and 1 cycle, starting from the circle and going round. So 1 cycle is essentially 2 pi radians. So this dimensional analysis tells us that when we take this 2 pi radians, right, and divide it by the period, because remember that this is 1 over time, so we have 2 pi radians in terms of 1 cycle, in terms of the time. So 1 over t, remember that's what frequency is. So this 2 pi over t is given the name. So this name is the angular velocity. So that's in radians per second. So this omega is equal to 2 pi over t. And we remember that 1 over t is just f. So we can write this as 2 pi f. So this is the reason why angular velocity omega and frequency are used interchangeably, because you can see that there is a direct correlation and that the only difference between angular velocity and frequency is that this 2 pi. So this angular velocity is just a constant factor of this frequency. So if we know what the angular velocity is, we essentially know what the frequency is. There's a direct proportionality between this frequency and angular velocity. So it's okay, it's fine to use these terms interchangeably, because if we know what the frequency, we just multiply it by 2 pi and we get angular velocity. So since they are directly proportional, a measure of angular velocity is a measure of frequency. So that's why many textbooks actually use these terms interchangeably. They'll talk about the frequency domain. So when they speak about the frequency domain, what they're actually speaking about is this angular velocity. It's a representation of the frequency, essentially. So they would represent functions in terms of this angle, because remember, this angle has a total period of 2 pi. So when I say angle, I mean a random point. A random point, we can call that theta 1, for instance. So if we say that theta 1 is the variable, and the total period of theta 1, if it were to be drawn on a sine curve, like that, then each point t1 corresponds to a point theta 1. So let's just say we have theta t1 there. So t1 is halfway along this cycle, and there you would have a theta 1 associated with being halfway along the circle. So it's a variable that's just changing. So how do we convert between theta 1 and t1? So theta 1 is simply omega t. Why is it omega t? It's because this angular velocity is radians per second, and it's a constant. So we take 2 pi, right, the total angle, and we divide it by this total time that it takes to complete this cycle, and that's of course the period t. So omega over t is actually a constant for this one revolution. So you can think of that as speed. And remember that speed times time is actually distance, right? So that's the way to think about it. So that's how we do this actual conversion here. So we would represent theta 1 to be the variable, and you can see that it's also related to time in this way here. So instead of considering our analysis to be in terms of this variable t, it's now omega t. So the whole purpose of this video was to draw the distinction between frequency and angular velocity. Many of the textbooks will also talk about components, specifically frequency components. What we do with the Fourier transform is that we take a normal function. We drew a function here earlier, this f of t, and we break up this function to be a sum of signals, right? To be a sum of different signals. And when we speak about a frequency component, so this is another term that's used that may be used in a lot of books but not explicitly defined. So when we speak about a frequency component, we're speaking about a certain function, whatever it may be, being broken up into a sum of many different signals. So maybe here's just a random function. There's t, there's f of t. And we can say that each point along this function, or whatever it is the case, we now take it, this entire function, its entirety, and we say that, you know, it's the sum of a whole lot of different signals. Better. We can have a very wide signal like that. Or we can have a signal like this. So you can see that this one has a very high frequency. So this has a high frequency, this has a low frequency, or whatever it is the case. And you can see that maybe they have different amplitudes, right? So we start thinking about a function being the sum of a whole lot of different signals, and each of these signals have their own frequency f, and an amplitude a. So if we know the frequency and the amplitude of a signal, then we have information, all the information we need about this signal. So this combination of this frequency and this amplitude is what's referred to as a frequency component. So these terms will be used a lot in the analysis of the Fourier transform, and this video just gives a simple explanation of all of these different terms.